Hey everyone, and welcome to today's Explainer. We've got a really cool topic today. We're going on a microscopic journey to figure out how solar technology actually works. We see solar panels literally everywhere now, right? On rooftops, on calculators, out in massive fields. But today, we're going to shrink down and look at exactly what is happening inside them to keep our lights on.
So here's the big question, and honestly, it's something we kind of just take for granted every single day. How does sunlight actually become electricity? If you think about it for a second, sunlight is just this raw, untamed energy pouring down from the sky. And a solar cell? Well, as we're going to see, it's essentially this brilliant little trap specifically designed by engineers to catch that raw energy and turn it into a usable current.
The magic of sunlight.
Okay, before we get totally lost in the microscopic weeds here, let's just step back and take a look at the macro perspective. We've got this massive celestial body, the sun, beaming down light, and we have these sleek, flat panels sitting securely on our roofs designed to catch it. But this magic doesn't just happen on the panel as one giant, solid piece of technology. Nope. A solar panel actually consists of many, many small solar cells. The entire panel you see is basically a grid. It's made up of countless tiny, individual energy traps, all wired up and working together in unison to generate power.
Section 2. The anatomy of a solar cell.
Now, this next part is super interesting because we are going to look under the hood. We're going to virtually stack the layers of this incredible energy trap, building it from the bottom all the way up to the top so you can see exactly how it's constructed. Let's walk through this physical build sequentially. Right at the very bottom, we lay down our foundation. This is a metal conductive plate, and it acts as our positive electrode. Sitting right on top of that is our vital semiconductor material, which is divided into a P-type layer and an N-type layer. And finally, capping off those semiconductor layers, we add an anti-reflective coating. You definitely want that there to make sure we're actually absorbing the sunlight into the cell rather than just bouncing it right back into space like a mirror.
All right, let's zoom in on those two middle layers because honestly, they are the absolute star of the show. We essentially have two very different chemical neighborhoods stacked right next to each other. Up top, we have the N-type layer, which is made of silicon mixed with phosphorus. And down on the bottom, we have the P-type layer, which is silicon mixed with boron. That distinct chemical difference between the top and the bottom, that is absolutely vital for making the whole trap work. And right where those two unique neighborhoods meet, we get this, the P-N junction region. It's the critical border region located directly between that silicon phosphorus layer on top and the silicon boron layer on the bottom. The crucial takeaway here is that this specific border is the exact staging ground where all the real action is eventually going to take place.
To complete our anatomy, we just have to add the very top layer, which is the negative electrode. And honestly, this architecture kind of looks like a miniature microscopic transit system. We got these thin stripes, cleverly called fingers, and we have thicker stripes known as bus bars. It's a highly organized grid laid directly over the top to help carry the current.
Section 3. The generation of energy.
Okay, we've built our trap. We know the exact anatomy of our cell. Now, let's see the physiology in action. The sun is out, and the sunlight is officially hitting the panel. When that light strikes, I want you to picture it almost like a microscopic game of billiards. Sunlight contains these tiny packets of energy called photons. These photons strike the solar cell and literally transfer their raw energy directly into the electrons resting inside that semiconductor material.
That sudden impact of intense energy, it forces the electron to instantly jump to a higher energy level. It breaks loose. It transforms into this highly active, highly energized free electron. But here is a critical detail that changes everything. When that electron jumps away, it leaves behind an empty space in its original spot, and we simply call that empty space a hole.
Now, watch where everything travels after that initial break. It's like a great migration. Those newly freed excess electrons, they move up into the N-type layer. Remember, that's the one with the silicon and phosphorus. Meanwhile, those resulting empty holes, they move down into the P-type layer, the one with the silicon and boron. So electrons up, holes down. They are completely separating across that P-N junction border we defined earlier.
Section 4. The flow of electricity. Because of this separation, we are perfectly primed for our final phase. This is the exact moment where all this microscopic movement of particles finally gets harnessed into actual usable power. Imagine the tension building up. Because of the constant barrage of sunlight, we now have a massive, massive collection of excess electrons gathering at the very top of our cellular trap, locked up in that N-type layer. They are agitated, they are highly energized, and they are desperately looking for somewhere to go.
And here is the catalyst. We provide an external supply, or we connect a circuit. By plugging a wire or circuit into the cell, we are essentially building a bridge. We finally give these trapped, highly energized electrons an escape route out of that crowded top layer.
Let's see how this builds to the grand finale. Those excess electrons enthusiastically rush out through the connected circuit. Why? Because they are incredibly attracted toward those empty holes waiting at the bottom in the p-type layer. They want to reunite. And that eager, rushing movement of electrons traveling through the external circuit back toward the holes, that very movement is electricity. That is literally the raw power lighting up your home.
Which really leaves us with this final, remarkable thought. How amazing is it that these microscopic jumps of tiny electrons, I mean billions and billions of them happening in a fraction of a second inside these clever little layered traps, are collectively scaling up to power our entire modern world? It is just a phenomenal piece of engineering. Thanks so much for hanging out with me for this explainer, and I really hope this microscopic journey completely changes the way you look at a solar panel the next time you walk past one.